Well, one of her friends described Betty Wood in an obituary as a Renaissance woman. Her life and career were filled with many interests, from iris gardening to teaching physics to ocean sailing, acting in plays, and also to her highly regarded expertise as a crystallographer, studying the arrangement of atoms within solid materials during her 24-year career at Bell Laboratories. She was an author, a speaker, an organizer of national and international conferences, and much more. She seemed to take every opportunity to write articles, books, pamphlets, letters to the editor, and so on. Well, March, as you may know, has been designated as Women's History Month. And so I think it is fitting to recognize Betty Wood's accomplishments in life in March 2022, which also happens to be 100 years after her birth. So let's begin with the next slide. Thank you. And just one slide of background on myself. I was born in 1955, and so these images were taken when I was 1.5 or 2 years old. My family paid a visit to Larison's turkey farm in Chester, New Jersey. I grew up in New Jersey in Fanwood. Here's my family at the time: my father, Joe, who's on this call, I believe, my sister, Susan. I'm the child on the right, petting the turkey, and my late mother, Nancy. We also visited Morven Museum, a visit I don't recall, but my sister came up with this lovely photograph from 1957. So it's nice to be back at Morven. So as you can see, we had an early connection with Bell Labs. My father worked at Bell Labs in Murray Hill, New Jersey, in semiconductor research. At one time when I was small, I thought he was a semiconductor of research, but it turned out to be semiconductor. In any event, we visited Santa. We saw the reindeer on the roof. We visited the dead room, also known as the anechoic chamber. We visited the laboratories and met some of the technical aides, and much more. We also saw a Picturephone exhibit in the mid-60s, right there at the labs in Murray Hill. I like to think that since I went into chemistry, that my father and his work provided an initial impetus, or at least in part, for my later interest in going into the sciences. Next slide. So let's talk about Betty. In a moment, I'll describe the 4 sections of this talk, but first a brief synopsis. As I mentioned, she worked at Bell Labs in Murray Hill for 24 years, starting in 1943. This particular quote comes from a history of engineering and science in the Bell system in volume 4 on physical sciences. The labs was doing research in ferroelectricity, semiconductor materials, lasers, magnetism, including ferromagnetics, and superconductivity. We'll get into a few of these topics later in the talk. Well, Elizabeth Wood was a close collaborator with many of the members of the technical staff at the labs, and they relied on her expertise and her insights about crystal structures, including some persons who later went on to become Nobel laureates. By studying materials by X-ray crystallographic diffraction, she helped to make possible the exploration of materials of similar types, but with different elements from the periodic table, using her knowledge of chemistry. So she played an important role, even if her name is not a household one. Next slide. Well, let's get into her background and education. And then we'll talk about her research and other initiatives, and a short section to conclude on awards and recognition. Next slide. Well, Betty was born Elizabeth Jean Armstrong in New York City across from Grant's tomb. She had the privilege of attending Horace Mann School for Girls in New York, which is, I tried to indicate with a yellow dot there. She also attended Barnard College near Columbia University, where she obtained her BA in geology. Then she went to Bryn Mawr College in Pennsylvania and obtained her Master of Arts and a PhD in geology and chemistry. After that time, she worked for several years teaching between Bryn Mawr and Columbia University and developed quite a range of expertise in the topics you see listed below, all of which she put to good use. Well, her education at Bryn Mawr College during her PhD studies was influenced by several women who were geology professors. Florence Bascom is thought to be one of the leading persons in the US to study geology and teach young women. It was a field that young women were going into, as well as physics and crystallography. Well, two of Florence Bascom's students were Ida Ogilvy and Dorothy Wyckoff. And these two women influenced Betty by teaching her crystallography during her graduate studies. She learned mineralogy and several related topics as well. As you can see, she died in 2006 at age 93. And we'll go on to the next slide. Thank you. Her PhD dissertation was about the geology of the terrain stretching between Bryn Mawr College on the bottom left. It's a bit hard to read, but this was a map from her dissertation, and Bryn Mawr College on the left, and then Trenton on the top right. In the lower panel, you can see the Delaware River sketched in blue, and the upper map is the region of the crosshatched smaller map down here, just to give us some idea of where she was working. So she traversed, probably on foot, all this terrain, mapping out the specific rock types. And she was interested especially in myelinization, which was in the title of her PhD dissertation. Myelinization is the kind of the fusing of rocks under shear stress. Up at the top indicates that she was also doing microscopic light microscopy to examine her rock specimens. And her PhD dissertation is very detailed on all these rocks and where they were exactly found. Next. Well, after a period of teaching that I mentioned, Betty goes to Columbia University in New York City for a year or two under a National Research Council fellowship. This was during World War II, and she, along with her advisor or mentor, Paul Kerr, put together this booklet of the past 100 years of quartz crystal preparation. And this would be artificial quartz prepared in the laboratory. It was important, evidently, to compile this information in order to share it with others who are working on quartz crystals for electronic applications like radio transmission and receiving during the war. The booklet was distributed in North America, but its use was restricted so that I think the enemy wouldn't get a hold of it. The editor's note indicates that this information might be useful to assist additional experiments. Next slide. Well, what is crystallography? One of the topics of this talk. It's a science that examines the arrangement of atoms in solids. That's a very brief definition, but let's look at some visual examples. If anyone's been to Trailside Museum in Mountainside, New Jersey, as I did as a child many times, you can see crystals of different types displayed there. Some crystals might even be displayed under a black light to see their fluorescence. Well, quartz itself is made of silicon and oxygen and falls under the hexagonal pattern of crystal formation as seen on the right in the middle left, hexagonal, and under that is quartz. There are many different types of crystal shapes depending on the chemical elements that make up a crystal and how those elements or atoms come together to bond with one another. Next slide. Well, let's look at a simple crystal, something we have on our table oftentimes, salt and pepper. Salt, as you may know, is made of sodium and chloride. The boxy structure in purple and green represents just a portion of a crystal of sodium chloride. At the top, they have plus and minus signs. That's because sodium donates an electron to chlorine, and we call it chloride. In reality, this grid of purple and green balls would extend much farther in space. Here's Betty's definition of a crystal. It's something composed of atoms arranged in an orderly, repetitive way. I like their subtle humor, as in many of her writings. Well, some features of crystals are a unit cell, which is the smallest patterned unit, repetition of the unit cell to build up the crystalline solid. We've all experienced crystals in some form or another, whether it's in a diamond ring or tourmaline, as in my niece's engagement ring. We could look up the structure of that if interested. Okay, next slide. Whoops, we have Na, a little bit skewed on the left, but this is the periodic table of the elements. And I'm just indicating some of the elements I've been talking about so far. Purple and green make up sodium chloride or salt, sometimes called rock salt. And as we'll see more of about quartz, silicon dioxide, one silicon and two oxygens, as indicated in the gray and red. We'll come back to the periodic table a little later on. Next slide. I'd like to go through with you some, but not all of Betty's research and close collaborations with other scientists at Bell Laboratories. Next slide. So Betty joins the labs in the physical research department, where she was the first woman scientist in that department. She started working at Murray Hill, even though she was still living in New York City. This is an image taken from a 1943 journal called Nature, but the labs, as I understand it, opened in 1941 here in Murray Hill, which was considered a rural location. Later on, the buildings and facilities were greatly expanded. But at the time, it must have been a state-of-the-art facility. Next slide. Well, she had a kind of a funny interview process. I'll let you read the quote here. But in essence, she was invited to interview because of her knowledge of quartz crystals. She was transferred back and forth between a woman and a man for her interview. Eventually, they agreed to hire her as a member of the technical staff. And some of you may know that phrase as MTS. So that was part of her history and some indication of the times during which she was hired. Next slide. Well, later on, this individual, Clinton Davison, sometimes known as Davy, won the Nobel Prize in Physics. He directed a crystal science team, and Betty participated in that team. At the time, there was a big effort at Bell Labs, Western Electric, and many other places for the development and design and production of quartz crystal plates, very thin wafers that were used in electronic applications, such as radio transmission and receiving in the thousands of tanks that were out on the battlefield, for example. So she was part of this team early on, working with a prominent scientist. Next slide. Well, here's where I have a lot more to learn. What is a piezoelectric material? Some of you could describe this readily, I'm sure. It's one that undergoes a transformation of electrical and mechanical energy, going from one state to another and back again. Well, contained in a sealed device for electronic applications would be a small circuit like the one shown in the box, or much more complicated ones. Here we can imagine the crystal in green, bright green, being stimulated by a voltage so that it resonates. In other words, it undergoes tiny motions like those shown on the right. It's flopping up and down. It's getting extended and in various different directions under the influence of the voltage. Well, the voltage is tuned so that the crystal resonates and has an output at a certain frequency. This one, 16 megahertz. The frequencies for radio were specified by the United States Signal Corps, and many tank sets were used. Let's go on to the next slide. Well, quartz itself is a mineral. It comes in many different forms and colors. We can see on the left. Its simplest formula is SiO2, or silicon dioxide. The red and gray boxy structure at the bottom right is one depiction of quartz or silicon dioxide. This cubic area would be repeated in three-dimensional space to build up the entire crystal. If it looks like there's air in between some of the atoms of oxygen and silicon, you could probably say that's right. There's space between the atoms, and the whole thing is very tiny. You can see the fraction of an inch. You can probably buy a piece of quartz at your local rock shop. Well, during World War II, most of the quartz, natural quartz, came from Brazil because it was a very high quality quartz and there was plenty of it. Also, since synthetic or artificial quartz was just being developed in a more prominent way during this period, natural quartz was still of interest. Later on, after the war, people switched over to artificial quartz for more applications. Well, I thought it was interesting that, and you can watch this film on YouTube, Brazilian Quartz Goes to War. Chunks of quartz crystals were graded and sorted in Brazil and shipped out of Rio de Janeiro back up to the US and other places. The map second to the left is showing a particular region of Brazil that had quartz mines, where men were digging with pickaxes and extracting the quartz. In the middle, we see a hand holding a tiny wafer that would go into a device. So you have to go from the big chunks of quartz and saw it down and etch the faces so they're flat at a particular angle along some of the axes of the crystal coordinates. Well, Bell Labs and Western Electric were major users, and this graph indicates, it's a little hard to read, but the exports from Brazil grew dramatically between 1910 and 1945. As you can see, peaking toward the end of the war. One other thing about this slide, Brazilian quartz was originally shipped on barges or ships, but some of them began to be sunk by German submarines, and then the shipments went by airplane. Next slide. Well, the tiny crystal wafers shown at the bottom here are called by different names, wafer or a blank. These were produced to function with precise frequencies. On the left, we see the mother crystal, or the chunk of quartz that you start with. It had to go through a number of steps in the laboratory or development lab, where it got sawed down into slabs, inspected, lapped, which was to kind of polish the surfaces, finish and clean, and do some testing to make sure it was working at the frequency desired. Well, Betty's X-ray diffraction expertise came in with the circled areas. So her work was important. Other people were working on this elsewhere as well, but everyone was contributing to the war effort. At Bell Labs, about 3/4 of all the employees were shifted over to wartime work. On the right, this was actually taken from a 1950s manual, but gives some indication of starting with the mother crystal, taking a slab out of the middle, and then it's very technical here with XYZ coordinates, but they could produce a bar, think of a brownie bar, and then take slices of it at the precise angle needed so that it would form a resonator. Next slide. Well, altogether, Betty had 3 patents. Her other 2 were in 1953. This one was applied for in 1945, and it had to do with indicating the quality of etching of a crystal plate undergoing manufacture. She's calling it a plural goniometer. It's measuring angles of both a crystal plate of interest and a standard or test crystal plate. And so there would be a readout at the ratiometer at the top of how well etched your crystal plate was. Next slide, please. So that was an example of her very detailed work to come up with new equipment and instrumentation to serve her projects. Well, shifting gears just a little bit, in the early 1940s, Bell Labs ran a series of articles on women employees. Betty is shown at the bottom left. She's there with her microscope at her desk. Most of the other women in this particular article were doing apparently secretarial work or mimeographing. As the war went on, increasingly women employees were put to work on some technical jobs having to do with the testing and quality of manufactured devices. I'd like to thank Joe Schott and my Aunt Marilyn, Dr. Marilyn Hart, for providing these copies of the Bell Labs record from that time. Next slide. Well, in 1947, Betty married Ira Wood, who was also working at Bell Labs. He came from Redlands, California, and obtained his degrees at Stanford. He studied engineering with Fred Terman, who was a key person in the development of Silicon Valley. Later, the labs hired him to come out and try to set up Silicon Valley of New Jersey, but it ultimately did not work out. So he was in transmission research, and he did some important work on projects, including the repeater for the transatlantic cable, and worked on some wartime projects as well. Well, he died in 1977 after the two of them were married for 30 years. But in the meantime, the two of them developed an avid interest in growing and hybridizing irises because they found some irises outside their apartment, and then bought a house in New Providence, or built a house rather, and set up a garden, joined different iris growing societies, and traveled around the country giving judging contests and writing many articles and taking leadership roles. Next slide. Here's another piece of equipment, a little different from the goniometer shown a minute ago. Betty published on a hot stage for a polarizing microscope. She needed this to observe the shifts in the shape of crystals. And I've tried to indicate with the blue to red arrow that a crystal at room temperature might have one shape, and this would be the the microscopic shape of a crystal unit cell, and it might expand under the influence of temperatures up to 800 degrees. This was important for working out the structure of new ferroelectric crystals, which can be used in capacitors and in memory devices. In these cubes and shapes, the titanium, as we'll see in a minute, is indicated in blue, titanium metal, and then oxygen and other elements forming the basic cubic shape. Next slide. Let me mention Betty's crystal orientation manual. These are still available through eBay and other places. It was a very important little book that has been used by generations of scientists. And she gets right into how to orient crystals, all different types of crystals, and according to what angle you want to peer at them using X-ray diffraction. On the cover is actually an X-ray diffraction pattern of tungsten. So I want to take just a minute to go through what we're looking at. You can see some symmetry of that pattern, which is kind of an aquamarine color. And the diagram on the right kind of explains what's going on here. If we start with number 1, X-rays from a tube are directed through a hole at a single crystal. And some of these X-rays are scattered back, deflected by the atoms in the crystal, and they're scattered back and impinge on the plate, making dark spots because it's a photographic plate. Now, the pattern that results, and you can kind of see a pattern emerging in this cartoon, although it's different from the one on the left. The pattern gives some indication of the arrangement of atoms inside the crystal and would be reproducible from one single crystal to the next of a given material. This is called a backscattering technique because the X-rays are bouncing back. There are other techniques for X-ray diffraction, but I thought I'd just mention one for today. Next slide. Well, what is a ferroelectric material? It's something that undergoes a change in polarization. In other words, its charges, positive or negative, inside the crystal are moving about and getting shifted from one orientation to another. Well, her colleague Bernd Matthias and co-workers were seeking new ferroelectric materials at the time in the 50s. Betty was called upon to use X-ray diffraction to figure out the structure and the quality of the new materials. And they reasoned that since perovskites, having the unit cells shown on the left, since perovskites having the formula AbO3, where O is oxygen, showed promise as ferroelectric materials, that they reasoned that perhaps other elements could be substituted for A and B in this formula. And here are a few in the green box that Betty worked on. I've separated the elements just to for visualization. Barium, titanium, oxygen, and in the middle we have sodium again, niobium and oxygen, then yttrium, aluminum, oxygen. Some of these elements are familiar to us, for example, from aluminum foil, aluminum metal, but others may be more obscure as far as the periodic table of elements goes. The beauty of this approach was that they could discover new materials by plugging in different elements or metals in this case, and finding out their properties and characteristics. Next slide. Well, another area in which Betty used X-ray diffraction was developing superconducting materials. These are materials that have no resistance or resistivity to the flow of electrons in the material below a material's critical temperature, sometimes written as TC, T sub C. Well, I'd like to point our attention to progress over the last 100 years or so in superconducting materials. There's a lot on this graph, but just to notice the general trend, which is going from the bottom left up to the top right, and indicating that as time progresses through the decades, that the critical temperature, or the temperature below which a material was attained superconductivity, became higher. And so close to the present time, and these are still developing and going up, people were seeking room temperature superconducting materials. The reason is that if you have a higher temperature superconductor, then you don't have to cool off your samples with liquid helium or liquid nitrogen, for example. And superconducting materials are used in magnetic levitation for trains or toys and other devices, and as well as in superconducting supercolliders for high energy physics experiments. Well, down at the bottom left, a few examples I pulled from Betty's publications, and often she had several authors on her papers, but sometimes she wrote papers on her own. Going down in the blue region, we see vanadium, gallium, which has a higher critical temperature than the ones below. So niobium gold, vanadium gold, different combinations of metallic elements were used to find higher temperature superconducting materials. Now the blue shaded region, this oval, shows roughly the period of time when she was working on these materials in collaboration with others. The superconductors have made a lot more progress in recent years, but at the time, she was contributing to their development slowly but surely. Next slide. Well, as a chemist myself, I couldn't help but put up a periodic table that includes roughly almost all of the elements that Betty worked on during her Bell Labs career. I did not put in the symbols, but the shading indicates that the blue were ferroelectric materials, orange superconducting. And she also worked on materials that were polymorphic, in other words, changed their shape under some stimuli like heat, and ferromagnetic. In fact, she came up with a material that was both ferromagnetic and piezoelectric. I forgot to mention that ferroelectric materials are really a subset of piezoelectric materials. Next slide. Betty had a number of papers concerning the standardization of how to write and talk about crystallography terminology. So here are a couple of examples. And she was known for the clarity of her writing and exposition. We can see in the top diagram, she's pointing out the different layers at a surface of a crystal. This became very important because, particularly in semiconducting materials, the surface layer, the atoms on top, have somewhat different characteristics than the ones below them, which are kind of in the bulk, you could say. And so here she's trying to aim toward a uniformity of nomenclature or naming of these different strata. Down below, she's illustrating with calcite a two-dimensional projection of a 3D crystal onto a piece of paper and showing how that can be done. Thank you. Well, her expertise was highly valued at Bell Laboratories. Bottom left, and some of you in the audience may recognize Carl Thurmond. Here he is discussing in an undated photo a crystal model with Betty. So I like to see her here apparently explaining something to a fellow scientist coming out of her expertise. Looks like she's got some rocks and other models up in the cabinet there. Philip Anderson in the middle, later won a Nobel Prize in physics. And I got some of this information from some of these individuals' memoirs or papers that were published, for example, by the American Institute of Physics or National Academy of Sciences. He says, I didn't know beans about either solid state physics or solid state chemistry or crystallography. And so that's where Betty came in to help him out. And burned on the right, Betty taught me crystallography. So apparently she was quite influential there in the laboratories. Next slide. I'll let you read this one on your own. So people would seek her out or encounter her on a long hallway. This is not the hallway at Bell Labs, but apparently, as I understand it, the hallway at Bell Labs, the very long corridor, almost had an infinity perspective to it. Next slide. The mid-1960s were a very busy period for Betty Wood. She was asked, and by one account, Lady Bird Johnson asked Bell Labs to have a woman scientist be on the receiving end of the call. But this project initiated the public use of the Picturephone in 1964. Picturephone was also displayed at the New York World's Fair in '64. I might have seen it there. Maybe some of you did as well. Well, Lady Bird Johnson initiates the call from the National Geographic headquarters in Washington, D.C., and Betty receives the call in New York City. You can actually hear some audio of this conversation on a YouTube from the internet. I'm afraid Lady Bird does most of the talking and doesn't let Betty say too much on the YouTube. Well, this Picturephone launch was not ultimately successful, although it was a forerunner of what we're doing right now, having conversations with video. It was launched again later on, but it was working at the time. It was just expensive and had certain limitations, like you had to pre-arrange a call and go to a certain office to make the call. Next slide. Well, Betty was very involved in science and in particular physics education and in scientific societies. Let's have a look. Next slide. Well, while she was at Bell Labs, she participated in teaching physics as part of the CDT program. also called Kelly College after Mervyn Kelly, president of Bell Labs in the late 40s. He was keen on developing solid state physics at Bell Labs. He really wanted to push it and thought that was the future. He was aiming at organized creative technology, nice phrase. Well, the idea was that engineers in particular coming out of colleges and universities may not have had enough science and background to participate in communications projects at the labs. So Kelly College was aimed at getting them more up to speed by having them learn physics, chemistry, and so on. Well, Betty was asked to teach atomic physics. It's not a topic she had particularly studied in the past, but she jumped at the opportunity and asked for a semester to prepare for her teaching and then put her teaching to use. I don't know how long she did that, but it was part of her lifelong participation in teaching science to others. Next. She also, while at Bell Labs, participated and wrote the script, as I understand it, for a film that came out in 1959, talking about crystals, one of her specialties. She worked with a film producer, and I understand from Sheldon Hawkheiser at the AT&T archives that this 16mm film exists, but it would need to be converted into a DVD for viewing nowadays. There were quite a few films produced at Bell Labs around this time, including by her colleague Alan Holden. Well, finally, another project while at Bell Labs, and once again in 1964, she did a lot that year. This was for high school students and college kids, and included real experiments to do with the kit components. Betty's kit was part of a series of kits put out by the Bell system called Aids to High School Science. There were other ones on topics like solar energy and several others. Well, her kit came, you can see at the bottom in the pouch is some bottles of chemicals, and she had specified all the small pieces of equipment needed to not only build your own microscope, but to grow crystals and examine them with light. Amazingly, this was very popular and was translated into several languages. Around this time, Bell Labs also had scientists going out into the high schools and demonstrating some of these kits. I don't know for sure if Betty went out to do that, but she did participate with the American Institute of Physics in school visits during this general period. Next slide. Well, she was very interested and adamant about promoting physics as a topic for a career for women. In fact, at one point, she gave a talk that was titled, "Why Shouldn't I Be a Physicist?" Here in the booklet, for which she received funding from the National Science Foundation, she describes various different careers like astrophysics and biophysics, gives several examples of career types, and also some of the hindrances that people were likely to run into at the time. After this booklet came out in 1962, she became recognized for, as I mentioned earlier, the quality of her exposition of topics and the clarity of her writing. She was asked later on to, even by organizations like UNESCO, to do some writing and summarizing of large amounts of data because of her ability to do that. Next slide. Few articles she published over a long period of years. Not only was she interested in teaching young people science, but also teachers. For a few years, she taught physics at Fairleigh Dickinson University in Madison, New Jersey. teaching elementary school teachers about how to teach physics. Next slide. She wrote many books, perhaps a dozen of them, and some of these became very popular. The books shown here are related. The one on the left in blue is Crystals and Light, about crystallography under the light microscope, or what you can do with crystals in light, and then experiments with crystals and light, which went into her kit. These were full of illustrations. She worked with professional illustrators, and one reviewer commented, "These are real experiments, not just things you plug in and get some result." Next slide. In addition, she summarized large amounts of survey data and collated them into books. I like the spring, or maybe it's a slinky, shown in the left image. These were for educators to learn how to teach better and to give them some ideas of experiments. Looks like on the bottom right, the black and white figure, someone is pulling a string through a block of ice or an ice cube, and having it melt and then reform as it goes down. So these books got wide use, and she worked with some of her crystallographic societies to publish them. Next slide. She wrote on a different topic, on airplane travel. Some of you may have seen this popular book. Now it has a slightly different title, but at the time it was Science for the Airplane Passenger. And she became interested in what you could see and experiments you could do while in flight. So she talks about meandering rivers, cloud formations, measuring the angle of the airplane at takeoff, and many things. The photograph shows her getting interviewed about this book. She also went on the Today Show to talk about it. Next slide. Well, here's a picture of the back of the book. The grid of pinkish reddish colors is a goniometer. It's kind of an instrument, or a graph in this case, that can measure angles. And she talks about in the book how you can measure the acceleration of an aircraft or the incline of an aircraft as it takes off. This was typical of her books and writings. She would include something that you could do actively. Like in an earlier book I mentioned on crystals and light, she included a piece of Polaroid film to do experiments with. Next slide. We're coming toward the end here. Well, after she retired in October of '67, she continued many writing projects, including to Barnard Alumni Magazine as a member of the class of 1933. And there at the left are all the women in her class. I've not identified her in particular. Maybe you could help me with that. But I liked what it says. She's working on 4 projects at the time of this letter. As an outgrowth of her travel book, she wrote a series of 6 articles that appeared in American Airlines in-flight magazine. And she was writing a booklet on crystals for school teachers that we saw for global distribution. And then she had just finished writing a booklet, probably with her husband Ira, on iris growing. It was said about some of these writings that they were really classics, that to try to update them would be pointless because she did such a good job in the first place with the writing and publishing of them. Next slide. Finally, in terms of service to the wider community, Betty served in leadership roles with a number of crystallographic societies, some national, some international. Here she is at the left in 1957, discussing maybe science and attending a lecture. And she was also president of the ACA, it was called American Crystallographic Association, in 1957. And some of these societies merged at one point, and she was instrumental in helping that to happen and writing the constitutions. Next slide. Now, finally, the first International Congress, shortened to IUCR as its acronym, back in 1948, she had helped launch this series of gatherings, beginning with this one in Cambridge, Massachusetts. I have circled her at the left. You can see that mostly men are gathered, but there's a scattering of women as well. Women were going into this field. At the far left, the far right is Kathleen Lonsdale, bottom right, who was an expert from the United Kingdom on this topic. Next slide. Finally, a short section on awards Betty received and also awards that she created. Next slide. She has a long list of awards, fellow of certain societies. The italicized awards were honorary Doctor of Science at 3 colleges and universities. That's a high honor. She received in 1970 an award from physics teachers and that association, as well as in the mid-70s with her husband Ira Wood. The American Iris Society awarded them a joint medal for all their contributions. And we'll see in a minute this last one, the New Jersey unit of recording for the blind and dyslexic, where for 30 years she drove to Princeton to record the science books for persons who were blind or otherwise could not read. Next slide. It's now called Learning Ally. She was giving back, and she, toward the end of her time reading books, she was driving a Prius down to Princeton from Red Bank, where she had retired. She said when they found out she was a scientist, they said, okay, you're not going to be reading any novels. We'd like you to read science books. And so she did, including some of her own. On the right, she's receiving an award. I'd like to find out more information about this, but it was for her outreach and service in this regard. Next slide. Apologize for the fonts overlapping. I was in communication recently with Nobel Prize winner, Professor Roald Hoffman at Cornell. He was the first recipient of the Elizabeth A. Wood Science Writing Award in 1997. And he said it was very special for him to receive this. He's a prominent chemist and also has written a number of books and plays. And we interact with him from time to time as part of my work at Northwestern University. The image at right is from one of his books called Chemistry Imagined. And Betty took the trouble to have the image put into a plaque specifically for him on the awarding of this honor. And she did that at least for several other winners in the coming years. This past year, it was Alan Alda who won the award. Next slide. Well, this finishes up the talk. There's been kind of an iris theme going through my comments. And on the left is the Betty Wood hybrid. A friend and colleague named this iris after her. The one in the middle was cultivated by her husband, Sandy Wood. And Betty actually had two hybrids, but I could not find their images. And at Wright, she helped to fund the creation and making of the metal design for the Morgan wood, given in honor of her husband and another person called Morgan. They went around New Jersey speaking and writing, judging iris contests, and even went to international conferences for years on end. They must have really loved this hobby. Next slide. Well, we're finishing up here. I want to thank Debbie for inviting me to give this talk. My father, Joe Schott, who worked at the labs. In fact, his service period was longer, about 41 years when you count in Western Electric and his Navy service. And he just turned 100 last month. I want to thank my sister Susan for providing some materials and photographs. Dr. Sheldon Hawkeiser, who helped me on a number of occasions with information about Betty Wood, although it's not that plentiful in the archives. Also Ed Eckert, who recently gave our family a tour of the wonderful technology showcase. And we had a chance to have some questions and answers with Ed. I highly recommend that tour when it gets open back to the public. Finally, some other resources are listed at the bottom left. Northwestern University libraries and their electronic databases were a huge help, as well as the print archives. Gotta love libraries. Finally, I'd like to thank you for your participation in this talk. And if time, maybe Deb has a short quiz for us.
Well, thank you so much. This was so interesting. Yeah, we do have a little poll. If everybody's ready, are you all set here? Poll number one. I mean, she's told us, but now let's see who paid attention. The science of crystallography deals with, and you have to pick one of these four. So click, whichever one you believe, the arrangement of atoms and solids, predicting the future, jewelry making, or digging up rocks and minerals. So everybody click in there and I will launch it right now. So just click your choice and we'll see who paid attention earlier in this program. Ooh, I think people really did pay attention. Okay, let's see.
It's good.
Well, yeah, it's not everyone has voted yet, but I'm going to give it another second or two if you want to vote. But okay, we're going to end the poll, and the answer is it's the arrangement of atoms in solids. So 100% of those who voted got that right. So good job, everyone. And then let me see. Oop, I believe I had another poll in here as well. No, wait. Yes, I do have Betty Wood poll number 2. And I will launch that one. Betty Wood poll number 2. Which of these materials is not made of silicon and oxygen? So let's see, all you scientists out there, which of these materials is not made of silicon and oxygen? Gonna give it a few more seconds on voters. Not everyone has voted. Don't be shy. Oh, we have, okay, good. Come on. Let's see some more voters. This could be a trick question.
That may be it, Deb.
Okay, here we go. And the results are 90% of you said graphite. Are they right?
That is correct. Very good. Graphite is made of all carbon atoms, and it's can be crystalline, but it occurs in layers of carbons. All the others have silicon and oxygen. So well done.
Cool. So everyone did pay attention. So let's head over to the chat here. And I'm sorry, not the chat, the Q&A. If you have any questions, please put them into the Q&A. And we have one here. Any chance that Betty knew another famous crystallographer, Rosalind Franklin?
Okay, very good question. Betty was, in fact, at conferences with Rosalind Franklin. And so she did know her. There were some prominent women crystallographers at the time. Rosalind, as you might know, is someone who probably should have won a Nobel Prize at the time when the structure of double-stranded DNA was awarded a Nobel Prize by Watson and Crick. Very interesting person, and she just had the 101st anniversary of her birth. And so there were a lot of conferences about that.
So we have another, actually, I've just received another question here. As a child, what encouraged her to go into this field? What drew her to the crystallography or the crystals as a child? Do you know?
Just what little I've read that I think some of her friends were going into geology, and it was known to be a good topic to study. Her work ultimately involved a lot of mathematics, physics, chemistry, and so on. If anyone else has an answer to that question, I'd be glad to hear it.
So just that others of her friends were studying that science, and so she went into that science.
Yes, I think it seemed like something as good as other topics, and she was inclined toward science. I don't know much about her early background growing up, but she must have been a keen observer of the world around her. So sorry for that vague answer.
So another question here, did she have any children?
She did not have any children. The family members that were left at the time of her passing were a niece and I think a nephew. Yeah, but no children for Betty. By the way, they got married in the cloister room of Riverside Church in New York City. And found an article in the newspapers about that at the time.
That's nice. Someone posted in the chat that they remember the video phone at the World's Fair, talked with a boy in Disneyland in California, and had the crystalline light kit when this person was in high school, and said, I don't think I paid attention at the time that it had been developed by a woman. Thank you for eliciting these memories. And another question, and this will be, I guess, our final question, unless anyone else posts one. Why, and this is obviously someone who knows a little bit about science, wants to know, why do voltage-tuned crystals oscillate?
Okay.
I'm asking you, not me.
Yes, I have a rudimentary explanation. Electronics is not my forte, but I understand that under the influence of electricity or a voltage, the piezoelectric effect will cause the crystal wafer to mechanically deform. Then it can only deform to a certain extent. And so the elastic nature of the material kind of forces it to go back to its original shape. But if a voltage is applied at a particular level, then the crystal can act as a resonator, deforming and coming back to its original in a very fast manner. Then, because also of the piezoelectric effect, which works both ways, the mechanical deformations cause an electrical signal that can be utilized in the form of oscillations. Sometimes these oscillator units were called clocks because of the regular nature of the motion of the tiny crystal. And it would depend on the type of slice you took out of the crystal, and also on how the device was put together and soldered.
Well, I mean, for saying that you were not an expert in it, you certainly did come up with a great answer. So, so thank you for that. And I want to thank everyone for being with us this afternoon. This was so interesting. And I invite all of you to come see the Ma Bell exhibition at Morven to get a little more about some other women in science and who were at Bell Labs. But we have met this afternoon, the first, and very, very well-rounded and so interesting. I also want to find find her iris. I want to find out more about that. So, and someone just posted here, excellent, thanks. I'm impressed. I'm not an expert either. So there you go, the person who asked the question. So
Thank you
thank
very
you
much.
very, very much. And you will all get a recording from today and a survey as well. So thank you so much, Peggy, and all of you. And we'll see you again next time. Have a wonderful afternoon.
Thank you, Deb.
Bye.